Today we'll be talking about an efficient way of cleaning the dirt in the room using wearable probability distribution and reinforcement learning to search for a path in order to clean the room in the limited amount of time fixed by a certain user. So today robots are beginning to play a great role in our society. In the near future they will be transferred in the real household to carry out many tasks. So the robot must start to interact with the environment and the real world in order to get used to how to manipulate the objects that are surrounding them. One tool that is allowing this robot to become smarter is machine learning. In this research, we are focused on domestic robots, especially vacuum cleaner robots. Actual vacuum cleaner robots employ a random methodical method to clean the room. The robot just moves randomly in the room in order to suck up the dirt. This method has two drawbacks. One, it cannot reduce the dirt level of the room below a certain threshold. And second, due to many obstacles that are present in the room, the robot must use a lot of type of sensor, ultrasonic or bump sensor, in order to avoid shocks. So it is very high cost. So in this research, in order to get a very good performance of the cleaning operation, we first estimate our dirt map of the room with a variable distribution. And with that dirt map, we search for a path for the robot to follow in order to clean the room very quickly. Our dirt estimation map, for our dirt estimation map, we assume that the variation of the dirt in the room is due to the air change rate, which happens when there is fluctuation of pressure in the room or exchanges of air between the interior and the exterior of the room, and the human activity in it. So, in our hypothesis, we model our dirt level with a variable distribution, and also we set a cycle for each cell in order to get the dirt level. For our dirt level estimation, we first estimate the dirt rate. What is the rate that is the dirt is changing in the room? So that dirt is estimated using a variable distribution, and the parameters are estimated using a gradient method and the data that we have gathered during our experiments. To estimate our dirt level, we suppose that our dirt level, it is a function of the dirt rate and the time of cleaning of a cell. After estimating our dirt map, the robot must find the path to follow in order to clean the room very quickly. So we can formulate our path planning problem as a reinforcement learning problem. So we use a DP network where we have as states the dirt map estimation in the robot position in the room, the action or the decision of the robot to move to the neighbor cells and clean them. And as goals, we want to maximize the dirt to time ratio for the robot to get the maximum amount of dirt in the limited amount of time. So in this figure we have our DQ network. It is divided into two parts. The position network, which has as input the position of the robot in the room, and the dirt network, which has as input the estimated dirt level with our variable distribution. These results are merged to output the Q value of each action that the robot is taking. Our goal will be to maximize the Q value of each action. as experiment, we use the room that is shown here on the left side, and the map is shown here on the right side. We also use a Panasonic robot which has two types of sensors. High-level dirt level sensors which can detect very big size, very small size of dirt, and a low-level dirt sensor which detects very big size of dirt. And on top of the robot we have LiDAR sensors which allow the robot to draw a map of the room or navigate in the room without bumping into obstacles. So we made many experiments on a daily basis. These are some sample of experiment. And here we have the dirt map taken during this day, and the red color show the density of the concentration of the dirt level in the cell at that time. So after estimating our dirt level with a variable distribution, we test our approach by first estimating the dirt map at a certain time, and with the dirt map we derive a path that the robot should follow. We train our network to find this path. So we simulated using RFVs, the path shown here in blue, and we test it in the real room, and as we can see, the paths are almost similar. So we set our robot to clean the room in 25 minutes, but it did it in 22 minutes. And we can see that the cleaning rate in the simulated environment in RVs and in the real world are almost equal, around 42. And we also compare our method performance with our experiment performance. We got a 5% of a degree of certainty of getting 90% of accuracy in our dirt map estimation. So in this research, we had two clear goals. One, which is the dirt map estimation, to estimate how the dirt is spread in the room, and a path planning, the search for a path for the robot to follow in order to clean the room very quickly. As a result, we get a very good poor performance concerning the dirt level estimation, but with a DQ network, we could see that it is a very efficient process for the robot to train the robot in order to follow that path. So to get a very good performance, in order to get better performance, we should analyze the air change rate and also start tracking people in the room in order to see how their activities are influencing the dirt distribution in the room.